So in here, I would like to explain our proposed research, which is applying deep reinforcement learning to improve throughput and reduce collision rate in wireless network. So here is the outline. So the first one I would like to explain about the introduction. Second one is applying deep reinforcement learning tools to 802.11 wireless network. And then the third one is our proposed method, which called as TANET. And then the fourth one is experimental design and methods, and then the last one is the conclusion. So first one is the introduction. Well, the popularity of the wireless networks result in the throughput degradation when a loss of nodes are transmitting the data packet. So if we are talking about the throughput degradation, we will talk about the increasing of the collision rates. So as a basic mechanism, there is a carry-sense multiple access with collision avoidance, or we can say CSMACA method, that relies by binary exponential back-off algorithm. So when the channel is sensed to be idle, it will wait several a random amount of time and its corresponding of the contention window. So the contention window optimization has significant impact on network performance. So as a collision avoidance technique, selecting the appropriate contention window size is very important. If the value of the contention window is small, the stations just need to wait a less time for data transmission. But the disadvantage is the stations have a higher probability to select the same contention window value, which will easily cause collisions. If the value selected by the contention window is large, it is not easy for the stations to select the same contention window value. Therefore, it will not cause collisions, but the stations need to wait for a long time to send out the packet. So in here, I would like to explain about the relative works that are relevant for our research. So the first one is Whitmansky and Schott. They proposing the centralized contention window optimization with deep reinforcement learning by using deep Q-learning network. Or we can say that is a CCOD-DQN. So in here, there is a figure 1 that explains about the CCOD-DQN topology. So they put the agent at the access point, and then the agent will just choose the appropriate contention window value to increase the normalized throughput. And then now we have the Ka et al. That proposing the smart exponential threshold linear, or we can say SETL algorithm. So in here, the contention window threshold is a fixed value, which equal to 512. If the contention window size in the figure 2, here, if the contention window size is smaller than the contention window threshold, which equal to 512, the contention window size will just adjust exponentially. But if the contention window size is bigger than the contention window threshold, it will just adjust linearly. So in here, our proposed method will just extend the contention window threshold value at different networks, at different wireless networks scenario, and we'll just compare with the CCOD-DQN. Okay, so in here is the objective. First one is in different wireless network scenarios, the contention window threshold is not easy to define. And then our proposed method, which is SETL-DQN, is proposed to find the appropriate contention window threshold value, and then to get a better throughput and lower collisions. So here is the second one, applying deep reinforcement learning tools to 802.11 wireless network. So here is the parameter that we will use for a DQN. We will use DPOMDP, or partially observable Markov decision process. So in here, we define the agent that located into the access point, and then we have the state, and also we define the action, the range of the new contention window threshold value from 128 to 1024, which equal to 2 square root of 7 plus 1 multiplied by 1 plus the action. And we have the transition probability and also the observation that we choose the collision probability for observation. And then the next one is the history of recently observed collision probability, which corresponding to current state and the previous state. And the next one is we have the reward, which we use the put that between 0 until 1. And then the next one have the gamma that corresponding to the discount coefficient. So here is the proposed method of us, which is the acetyl-Dickert algorithm. So in here, I would like to explain in detail about the acetyl algorithm. So in here, we have a fixed value, which is the contention window threshold value, which is 512. If the contention window is smaller than the contention window threshold, we'll have the collision that multiply by 2. But the success, and then the success transmission will have divided into 2. If the contention window is bigger than the contention window threshold value, the collision will just add it by the 32. And the success transmission will just subtract it by 32. Okay? So how about the acetyl-Dickert? So in acetyl-Dickert, we will put the agent at the access point, and then the agent will just choose the appropriate contention window threshold value by observing the collision rate based on the history of collision probability at the current state and the previous state. Okay, so the next one is the experimental design and method. So here's the algorithm of our proposed method. So the first one is this is the notation. There is a history of recently observed collision probability. There is a log that data science since the last interaction, and then there's a previous action, state, reward, and then of course there is a contention window threshold. So in our algorithm, we divide into 2 procedures. The first one is learning procedure, and then the second one is the evaluation. So here is the learning procedure. So in the beginning, we set the contention window threshold value become 128. Okay, but at the learning phase, the contention window threshold will just adjusting because of the exploration process. Okay, when the exploration process is degrades, it will just enter the exploitation process that based on the evaluation process. And then at this part is this procedure, it will just choose the appropriate contention window threshold value. Okay, so in here is the experimental setup, and here is the parameters for a DQN algorithm, and then here is the acetyl-Dickert topology that we will propose, that we have proposed. Here is the access point that the agent is located in the access point, and then there is they will observe the collision probability that interference for the updated the contention window threshold value, and then the access point or the agent will just broadcast the contention window threshold to the device, or we can say it become the stations. Okay, so the next one, here is the experimental results. So in the beginning, I say we would like to compare with the acetyl-Dickert and the CCOD-Dickert, right? So in here, we define the stations between 10 until 150 in interval 20. Okay, so in here we can see the acetyl-Dickert adjusting until 150 stations linearly, and then here we can say at the CCOD-Dickert, when the like network loads between stations 10 until 70, this contention window value will just adjusting exponentially. But at heavy network loads, the contention window value is choosing the maximum of contention window, which equal to 1024. So we can say that the CCOD-Dickert at the heavy network loads situation, the CCOD-Dickert cannot adapt to the heavy network loads situation. Okay, and then the acetyl-Dickert can adapt until the heavy network load situation. Okay, and then so what's the point? The point is the acetyl-Dickert can have the smaller waiting time before transmitting the data packet. Okay, and then the next one is the experimental result for the collision rate. So in here, I'd like to explain about the collision rate comparison. Here, there there's a legacy CSMACA, or we can say BEP, or binary exponential backup algorithm. And there's a CCOD DQN, and we have this SETL DQN. So we can see here the CCOD DQN and SETL DQN dramatically can reduce the collision rate. And we can say here SETL DQN can slightly bigger than the CCOD DQN. But even like the SETL DQN still can drastically reduce the collision rate rather than the legacy CSMACA. And then the next one here is the experimental result of the normalized throughput comparison. We can see here that the SETL DQN and the CCOD DQN at the light network loss from the 10th station and the 70th station, the result of normalized throughput is similar, right? But at the heavy light network loss from 90 until 150, the SETL DQN can have a better performance rather than the CCOD DQN. So here, the conclusion that become our last part. So here, the contextual without threshold value optimization can avoid excessive transmission delays before sending out the packet under light or heavy network loads because the contextual threshold is adjusting linearly. And then second one, the collision rate comparison make SETL DQN adapt quickly to the heavy network loads. And then the third one is normalized throughput of SETL DQN shows the outperformance over related backup algorithms, which is CCOD DQN. So that's all from me. Thank you.
好，英文讲得很好哦。